Hi class, we're on 6.1b. This is balanced equations. A balanced equation represents a chemical reaction, which is what we're going to be learning more about and how to do them. In this image, methane molecules combine with oxygen to form carbon dioxide and water. So in a balanced equation, the number and the type of each atom are the same on both sides of the arrow. So in this case, when describing a reaction, we begin with the identities of the starting materials and the products, without knowing the ratio in which the reaction takes place. Iron can react with oxygen to form iron 3 oxide. That results in rust, which is the reddish brown that we see on, outside on nails and stuff. In order to describe this process, we could write the equation as shown. But if you notice, we have 2 oxygens on one side and 3 on the other, and that doesn't make sense because remember the law of conservation, we can't have that. We need to have nothing is created nor destroyed. So we can't have 2 on one side and 3 on the other. This is something that is not balanced, and that's what we're going to learn is how to balance a reaction. So in order to accurately describe this reaction, we need to balance it to account for each atom of the starting material consumed and the products produced. And we do that by adding coefficients in the front. The coefficients are what are in front, and if there's nothing there, then it's defaulted as 1. Okay, so we're going to practice this. So the first step in balancing the equation is to identify the number and the type of atom on each side. Sometimes it's helpful to construct a table. I still do this to this day. I always write a table underneath, and what I tend to do is write them in the order that they come like this. So we begin with 1 iron atom and 2 oxygen atoms, and we have 2 iron atoms and 3 oxygen atoms on the right. We never, ever, ever, ever change subscripts. You can never change these little tiny numbers. If you do, you are changing what the molecule is. If you change this to a 3, you now have ozone. You don't have oxygen. So you can't do that. We have to only use the coefficients that are in front. All right. So we're going to start here by looking at oxygen. We have 2 oxygen atoms on one side and 3 on the other. So in order to balance, we add a coefficient of 3 to the left and 2 to the right. And this gives us 6 oxygens in total. So if you see here, we have 2 and 3, but by adding a 3 on one side and a 2 on the other, that gives us 2 times 3 is 6. 2 times 3 is 6. So we have 6 oxygens. But by doing that, we've also changed the iron atoms. So we now have 4 iron atoms. So by adding this 2, we have 4. But we can easily write a 4 here, and that balances everything out. This is an error. I meant to remove these X's. See the little green marks in front, and pretend that that's what you're seeing. So we have 4 iron atoms, 6 oxygen atoms. We have 4 iron atoms and 6 oxygen atoms, and the subscripts have not changed. So now we're going to try a harder one. And so when we're balancing equations, we are adjusting the ratio of the starting materials and the products. We are not altering the identity of the substances, which is why we do not change the subscripts. So let's try this one. It's a little bit more complicated. Now your book doesn't talk about it, but what I tend to do is I balance the metals first, because metals are usually, as we go on, it will get harder. But for now, they are not, I don't want to say never, they are not alone. They're not like this. They are always attached. Again, I don't want to say always. They are attached in a compound. And because of that, they're easier to balance. And we balance the lone elements by themselves at the end. This tends to be a general rule because it tends to make them easier to balance once everything else has been balanced. And it kind of ties everything together. And I will show you examples of what I'm talking about if it does not make sense right now. So the first thing we're going to look at is on the left side, we have 2 aluminum atoms, 3 oxygen atoms, and 1 carbon atom, and 2 chloride atoms. On the right side, we have 1 aluminum atom, 1 oxygen atom, 1 carbon atom, and 3 chloride atoms. Obviously, this is not balanced. So again, as a general rule, we tend to balance lone atoms or elements last. So chloride and carbon will be last. And that is because they tend to tie the whole balanced equation in together. So this means that aluminum and oxygen will be balanced first, and that's because they only appear in this equation in a compound. They're not alone. So by balancing aluminum, we have 2 on left and 1 on right. So we add a 2 coefficient in front of aluminum chloride. That now gives us 2 aluminum atoms and 6 chloride atoms. So in doing that, we have, I apologize that this shouldn't be here. This 3 snuck in. I think I made a few mistakes on this slide. I was trying to break these steps up and I probably goofed a little bit, so I apologize. You're not supposed to see this. So by adding a 2, we change this to 2, and it also changes 2 times 3 is 6. So then we can go on this side and add a 3, and that gives us 6. So we've actually balanced aluminum, which as these start getting harder, guess what? You will actually have to go back and forth and change something that's balanced to balance something else. So once you have it balanced, doesn't mean it's set in stone. You may actually have to go back and balance it again. All right, so after that, we now can look at another compound on here. So if we look at oxygen, we have 3 oxygens. So we can add a 3 here, and the 3 adds 3 to a carbon and 3 oxygen. So by doing that, we now have 3 oxygen, but we only have 1 carbon. This is why we wait till the end to balance the ones that are by themselves. Because now we can add a 3 to the carbon, and that leaves us with 2 aluminum on both sides, 3 oxygen on both sides, 3 carbon on both sides, and 6 chlorides on both sides, and this balances the equation. I have some examples, so if this seems a little confusing, I do my best to break it down. Okay, so I'm going to teach you this slide. I don't like this slide. I actually thought of removing the slide, but then I thought maybe it might be in your homework, so I'm going to show you, but I'm also against it. I don't have any control what Achieve gives you. I think I've already been honest that the chem department controls everything in this class. I do not know how to balance like this, so I don't agree with this, but I'm going to tell you what it tells me how to do this. So if you have polyatomic ions, it's not a bad thing. I actually know professors that balance this way. This is how they learned how to balance. I have never learned how to balance this way, so I would never do it. So you have nitrite ions and you have hydroxide ions. You have them on both sides, and what they're telling you to do is balance just the nitrite ions and the hydroxide. So you notice you have 2 here. So you put a 2 in front of the sodium nitrate. And you have 2 here of hydroxide. So you add a 2 here. Now by doing that, as long as the ions haven't changed, this should balance the whole equation. So this means that you have 1 nickel, you have 1 nickel, you have 2 nitrate, you have 2 nitrate, you have 2 sodium, you have 2 sodium, you have 2 hydroxide and 2 hydroxide. And this is a balanced equation. I don't do this. I don't know how to help you do this. I have always separated every atom on its own. That's just how I know how to do it. But again, I do know professors that know how to do this, and this is how they teach how to do it. I'm just not one of them. Not saying it's wrong. If you want to try it, by all means, but it's not something I know how to do. Okay, so now when we get to balancing equations, there is a weird kind of thing that can happen in equations, and you don't know about it till you're actually starting to struggle. And then you realize something's not right, and that happens very often. This is that we have to use a fraction in order to balance certain types of equations. They are not easy, but you can look for them and you can kind of count the signs of them, of what to look for. So when you're dealing with diatomic molecules, sometimes you're going to end up with an odd number. And when you deal with an odd number, you will spend hours trying to balance this, and it's not going to work. I mean, you will eventually get it if you keep going, but believe me, it's not worth it. There is a shortcut how to do this. These equations look just like every other equation. So it's deceiving until you start struggling. So this is why I want to point it out. It usually happens with oxygen by itself or hydrogen by itself. These are the ways to do it. So I'm going to show you, and I have an example. So basically you're balancing this out, and then you realize you have 7 oxygen atoms on this side. That's the first key. You have an odd number of oxygens, and it's a lone element or atom, diatomic. And it could be hydrogen, not just oxygen. So you add a 7 here. Now the next thing you need to do is divide that 7 by 2. Just put a 2 underneath it. Now what you're going to do is you're going to put a box or square brackets times 2. And what you're going to do is you're going to multiply every single thing in this reaction. By doing that, that will cancel out the 2 because you're going to have a 2 here, and those 2 will cancel out. So when you're done with this, you have a 2 in front of this, which is ethane, You have the 2 has canceled out, which gives you a 7. You have 4 in front of the CO2, and you have a 6 under next to water, and this completely balances. So it's a trick, and most books don't teach it, so I actually like that Achieve has discussed this, because most books have students struggle, and I don't know why. And the key thing is, you have a lone diatomic element, could be, it's usually hydrogen or oxygen, and you have an odd number of whatever this lone one is. That's when you divide by 2, multiply everything, and that will get you balanced. Okay, so I pulled my slides from another course. This is my list of how to balance an equation. Some of this stuff is a little bit more advanced. We haven't covered it yet in this section, but it's going to come up in the next section, which is why I'm introducing it early. So then when I cover that, it makes more sense. So here you write a skeleton equation with the correct chemical formulas for each of the reactants. If an element occurs in one compound on both sides, balance it first. That tends to be metals, then nonmetals. Hydrogen and oxygen tend to be last because they tend to be the diatomic lone gas. If an element occurs as a free element on either side, balance it last. That will be the key to tying everything together. If a balanced equation contains coefficient fractions, change these into whole numbers by multiplying the entire equation by the appropriate factor. I call it the 2 times half balanced reaction. That's just the name I've given it, like what I just showed you what to do. Check equation is balanced by summing the total number of each type on both sides. And trust me, this isn't always easy. I have made a small mistake and ended up spending hours on one balanced reaction because it gets crazy. If you start stressing, stop 5 minutes and come back, because these things will drive you crazy, and it's usually just one minor thing. Okay, so these are slides from another course, and I'm just going to go through and show you. Write an equation using the correct formulas for reactants. So we haven't covered phase changes yet, or phases. That's in the next section. But I'm putting them here to just introduce you to them. S means solid, so that's what these mean. And they are very vital in chemistry to know what you're dealing with. So in here we have aluminum plus sulfur equals aluminum sulfide. So we're going to count the atoms. So we have 1 aluminum atom and 1 sulfur atom. We have 2 aluminum atoms and 3 sulfur atoms. This is obviously not balanced. So we want to add some coefficients to change and make sure they're balanced. So we add a 2 here. And why would we add a 2 here? Because you see in the subscript, it's 2. So we can add a 2 here. So I add a 2 here, and I add a 3 here. So we have 2 aluminum atoms on one side, 2 aluminum atoms on the other. 3 sulfur atoms on one side and 3 sulfur atoms on the other, and this is now balanced. Okay, state the number of atoms of each element on the reactant side and the product side for each of the balanced equations. So this is to help start understanding what we're looking at. So we have phosphorus, and we have 4, and we have bromide, which is diatomic, but as a liquid, and this means gas. So here we have 12, and here we have 4, and we have 12. So this is a balanced equation, and this is a good way to start understanding how to look and read these. All right, state the number of atoms of each element on the reactant and the product side. So here we have 2 aluminum, that's a solid. We have iron 3 oxide, so we have 2 irons. We have 3 oxygen, and on this side we have 2 irons. We have, 2 aluminums, 2 irons, and 3 oxygen. So this again is a balanced equation. Okay, so now I am giving you a slide that you guys have not covered this information yet. So don't get caught up on what I'm about to show you. Just focus on the balancing of the equation itself. Eventually, you will have to do exactly what I'm showing you on this slide by pulling the information out, putting it into an equation with the phase, but we're not there yet, so don't overwhelm yourself with that. Just look at the balancing of the equation. Balance the chemical equation when solid iron 4 oxide reacts with hydrogen gas to produce solid iron and water. So we first write an equation. Again, you are not here yet, so don't worry about that. So here's the equation. Let's pretend you're given the equation. We haven't covered phase changes yet, so don't really worry about those. But this is just telling us that this is a solid, this is a gas, this is a solid, and water is a liquid. That's all this means. Okay, so now we want to balance this. So we're going to start balancing out. Let's start with iron. So here we have 3 irons, we have 4 oxygens, we have 2 hydrogens, 1 iron, 1 oxygen, and 2 hydrogens. All right, so now let's start with iron. This arrow should be closer. So I have 3 here, so I'm gonna add a 3 here. Yes, this is lone, and I don't like doing lones. The problem is this is a metal, and I tend to do metals first because they don't have the problems that a diatomic. This too messes everything up, and that's when you have to do the fraction. So this is by itself, so 3. Now we're going to take care of oxygen. We have 4 oxygen, so I'm going to add a 4 in front of this water, and that's going to give me 4. Now by doing that, I have to adjust. So did you see that I also adjusted hydrogen when I did that? So I adjusted the hydrogen, and now give me 8 hydrogen, but I still have 2 on this side. So by doing this, I can now easily see that I have 8 hydrogen. So I need a 4 to multiply by 2, and this should be 8. This should not be 4. This should be 8. That's an error. So that's 8 here. So let's see if I fixed it. Oh, I said by 2. I really explained it here. So we have 3 iron atoms, 4 oxygen atoms, 8 hydrogen atoms, and 8 hydrogen atoms, and this is a balanced equation. Okay, here is that 2 times half trick that I just covered in the sample. I'm going to show you guys how to do this. So, and I break this down step by step. Write a balanced equation for the combustion reaction between liquid octane, a component of gasoline, and a gaseous oxygen to form a gaseous carbon dioxide and gaseous water. Those are explaining the physical states. So you're not here yet, but when you will have to pull this out, this is a liquid, this is a gaseous, so it's mean gas, this means gas, this means gas. So those are the physical states when you write this out that you're going to have to, and that's what I'm highlighting for another course. You will get here, you will have to do this, but we're not here yet. So, but I want to introduce you to it. So in here, I've already put the reactants, the phase for the reactants, and now I have the phases for the products. And I'm going to pull everything out. So I have 8 carbon, I have 18 hydrogen, and 2 oxygen. I have 1 carbon, 2 hydrogen, and 2 plus 1 equals 3 oxygen on one side. Now, we know that this is going to be that fraction one, but you don't always know it. So that's why I'm saying look for the keys of stuff. It usually deals with the diatomic molecule of hydrogen or oxygen usually, and you're going to end up with an odd number, and you're going to have to fix it because of that odd number. Okay, so the first thing, let's fix carbon. So I have 8 on one side, I'm going to add 8 on the other. And this is a perfect example where I'm going to have to jump back and forth and fix numbers that are already balanced, because it's going to offset the more I try to balance something that's attached to. So I have 8 and 8. But now I've actually knocked the oxygens out of whack. They are different values. But right now we're focusing on carbon. So we have 8 and 8. Now we need to fix hydrogen. So we're going to fix the hydrogen first. Why am I not fixing oxygen? Because it's by itself. So we're going to leave that alone until the very end. So in this case, I need to fix. So we have 18 hydrogen on one side. So how do I get 18 hydrogen on the other? I add a 9. So 2 times 9 is 18. So I have 18 and 18. Okay. Now we're going to fix oxygen. So I have 16 oxygen here and have 9 oxygen here. That gives us 25. There is that weird odd number. Okay. Now we've got to do the rule to get this into a fraction. So what do? We do the 2 times half trick. That's what I call it. That's what I'm naming it. It just tends to help me explain it. So we are going to balance this by writing 25 here. So I have 25 here. But now what's the problem? I have 50 and I have 25. So that doesn't balance. So something's wrong, right? Well, that's when we do the half trick. So I am going to make this by 2. Why am I making it by 2? Because I want to get rid of that 2. But in order to do that, I have to affect everything else. So now I have 25 and 25, but we do not deal with fractions. So I'm going to multiply everything by 2. Everything, the whole thing will be multiplied by 2, and that will cancel that 2 out. So by doing that, let's show you the after effect. So I have a 2, I have 50, I have 16, and I have 18. And if you add these all up, this is 16. That's 16. Hydrogens, I have 36. Hydrogens, I have 36. Oxygens, I have 50. And adding these together is 16. Nope, not 16. What is it? It is, this is 32. So I apologize, I didn't fix this, son. This is 32 plus 18, and that equals 50. So pretend this is 32. 32 plus 18, I don't know how I didn't catch that, is 50. Now this reaction is balanced despite my error here. So hopefully that makes sense of breaking it down. Yes, it can be a little intimidating. Just stick with what you know and how I'm telling you how to do it, and you will be fine. Okay, so your book is giving me this sample. It wants you to count and then describe what's the best equation. So you're going to count all of these. So there's 2, 4, 6, 8, 10. And these are 2. Wait, no. 2, 4, 6, 8, 10, 12. But there's 2 of them, so that means 6, right? So only when I see this 6 here. And then you've got 1, 2, 3, 4. So 4 borons. So let's see if that is right. And I'm right. So get comfortable. Your book seems to like this, and you're probably going to get some like this in homework. So just look for what makes it easy. Remember, these are diatomic. They're attached, so count them and then divide by 2. That's going to give you the number that you need, and hopefully that might help you answer these, because you definitely don't have 2 of them. That's not going to work. It doesn't come in 6. It's a diatomic. There's more than 3 here, and it's a diatomic, so this doesn't exist. So process of elimination will help you